YouTube, Woo! Mr. King coming at you live from the studio. Here are the questions for the day. Please pause the video now and answer them. Next, remember, check your email about going back to school. Both you and your parents should have gotten an email. And today you'll be able to discover new patterns in the periodic table. So can you go to classwork? Go to Tuesday. Periodic trends Gizmo. We did it last week. Now we're going to do part 2. First thing, click here to access the Gizmo. And as always, it'll ask you to log in to get rid of the timer. And something to note is I have my login saved on my computer, so I never have to type it in again, which is really convenient. Next, click launch, little spaceship. And you may remember this Gizmo from last week, but it's going to be a little different now. So we start with hydrogen, the simplest atom, but instead of learning about the radius, you're going to click on Ionization Energy. And if you want to learn more about ionization energy, click on slide 2. I will give you a summary though. Ionization energy is basically how good an atom's security is. Okay? So the ionization energy is how much energy you need to steal an electron. So let's check out hydrogen versus lithium. So hydrogen, what you'll do, you'll grab it and see how much energy it takes to steal this electron. Remember, the positive wants electron because the electron is negative. And it's a lot easier to steal electrons from the atom because they're on the ring. So keep dragging until, boom, hydrogen lost the electron after the positive charge put in 1,312 kilojoules. So that's how much energy we needed to steal an electron from hydrogen. And let's see what happens when we do it with lithium. So here's lithium. Oh, it only took 520 kilojoules to steal the electron from lithium. So you can think of it like my analogy. Hydrogen has really good security. The robbers had to spend $1,312 to steal from hydrogen. Whereas for lithium security wasn't so good, so it only cost $520 or 520 kilojoules to steal from lithium. The first table will ask you to keep going down and see what happens to the ionization energy as you go down the periodic table. Yep. And then the next one, you need to see what will happen if you go across. So if you go from lithium to beryllium, then boron, then carbon, then nitrogen, then oxygen, then fluorine, what happens as you go across? Does the ionization energy go up or down as you move across? And how does it change as you go down? That's what the first part asks you to do. Next, we're going to learn something that's very similar. Electron affinity is energy released when an electron is added to an atom. This energy is always expressed as a negative value. The greater the magnitude of the negative value, the more attracted the element is to electrons. So remember that. The bigger the value, the more attracted it is to electrons. So you're going to do it again. So let's see the electron affinity for lithium. Lithium, as you remember, is really weak. It had a really weak attractive force. Let's see how bad it wants an electron. It only released negative 60 kilojoules of energy. So it didn't really want an electron that bad because it only released negative 60 kilojoules. Well, as fluorine, let's see how badly fluorine wants another electron. It really wanted this electron. It released negative 328 kilojoules. So lithium didn't really care for another electron. I had to get it really close. Whereas fluorine, it really wanted the electron, so it didn't take very much to get fluorine to steal another electron. Yep. So now you're gonna do tables 6 and 7 for electron affinity now. That's the last thing you'll do. We'll do the summary tomorrow. Okay? So try and get to slide 7 tomorrow. Thank you so much, everyone. Have a great day. Bye.